Welcome to this presentation on a deep dive with OmniML. Before we start, I'm just going to go through thanking some of our sponsors, without whom these sessions would not be possible. So thank you to all our strategic partners for committing to take tinyML to the next level together. One point, we have several areas where you can engage with the tinyML organization. We have, through Meetup, a series of meetups around the world. You can go and check these out on Meetup. We also have a LinkedIn community, so please join us on LinkedIn. Follow us on LinkedIn. And we also have a YouTube channel with all of these sessions, all of the history of all of these sessions, which is a great resource for you. We will be having a in-person live tinyML EMEA Innovation Forum, which will be happening in October between the 10th and the 12th. Please go to our site to have a look at that and see if you can sign up for it. And the call for presentations is actually closed now, but if you've still got presentations, please send them through. Perhaps we can squeeze you in. Today, we're going to hear from Diwu, who's the co-founder and CEO of OmniML. And he's going to do a deep dive into the OmniML tools. So I'll pass it over to Diwu now.
Great. Thank you, Martin, for the introduction. I'm very happy to be here. So let me give you guys a deep dive about our technology and the product. So the topic today is introducing Omnimizer, our first product, and then to show you guys how we use it to adapt neural network for the hardware to unleash the full potential of any hardware, generic hardware, microcontrollers, not just special accelerators for AI. And then in the beginning, I'm just going to give you a very quick introduction about our company. OmniML was founded in last year, May, by the leading experts in efficient deep learning, including Song Han and Huizi, who are the co-inventor of the deep compression and technology. And Song has been very active in the research area, being associate professor at MIT, pioneering in model compression and many other efficient deep learning technologies. Myself came from Facebook, used to be a tech lead at PyTorch, working on hardware accelerators. And we were backed by GGV Capital, who leads our Series Seed back in March this year. And also we're joined by Qualcomm Ventures and a few other Silicon Valley VCs. Our headquarters is San Jose, and we have 22 people across our main office at San Jose, as also Boston and New York. Just to give you guys some background, OmniML came from very deep technology or academic route, all the way starting in 2015, where Song and Huizi and their professor at Stanford, Bill Daly, they wrote this paper, Deep Compression, right, which has been kicking off this booming of model compression, pruning, quantization, so on and so forth, and many academic research. And since Song joined MIT, he then came up with works like Proxilus, NAS, and Once for All, with a bunch of other, efficient deep learning technologies. So that is the root of our founding team, and also is our technology root for the company. We're actually also, deep rooted with the tinyML community. Back in March this year at a tinyML summit, we actually came out of stealth during the summit. We launched the company. We tell the world for the first time what we do, what is our team, what is our vision, enabling AI for all the edge hardware. And these technology, including like MCUNet and proxyless NAS and training once for all network, where we can explore a vast design space of neural architecture space with only incremental training costs, reducing the carbon footprint of this massive exploration of training down to just a tiny amount, right? So definitely this is where our vision lies, and also where our company is rooted. And so then come into the problem is how can we leverage this technology for in the world of AI today. So today, in many different markets, AI is becoming a differentiation factor. For example, in ADAS, right? AI performance of AI, accuracy, the speed, the cost is absolutely crucial for the safety, for the functionalities, and basically is a key for the whole product. And there's constraints, right? So there's the hardware has to run on the car. It cannot be unconstrained. We cannot have constant link to the cloud. So that just poses a lot of additional challenges for deploying AI. Similarly for robotics, right? So it's again a constrained device. IoT devices, we're getting smaller, and also this new AR/VR, where device is small and then the computation requirement is absolutely massive. And so in all of these new markets, right, where AI has to run on the edge, deployment it remains to be a blocking factor. There's a lot of advancement in AI algorithm, right? There's so many good there's a new algorithm coming out every week, every month. However, deploying these algorithms onto these devices, these diverse devices, still a big pain points among the entire industry. One of the big gap in the deployment is actually the mismatch between the training and then the inference, right? We all know that the booming of AI is absolutely linked with cloud as well as GPUs, especially NVIDIA GPUs, right? People design the model and train the model in the cloud using massive cluster of GPUs. And as a result, right, so the architecture of these models or the design of these models have been evolving organically, unconstrained for these platforms. Now, when we have to inference, we have to deploy these models. Now we have to deploy these models onto diverse hardware platforms like embedded GPUs, robotic platforms, or even mobile phones. These models doesn't fit anymore because they were designed for the GPUs. So that in turn causes long time to market, long design time, long iterations, and also performance gap. It's hard to close, and people have to sometimes use higher version of the hardware, which is high cost. And finally, there are people. In order to do this, we need people to know both the AI algorithm as well as the hardware. For example, people have to know CUDA, people have to know embedded system, and they have to know about AI in order to do this well. So that in turn makes a team very difficult to scale, right? We have to hire a lot of the edge companies. We think, no, we have to do this well. We need to spend 2 to 3 years. We need to hire a very good team of engineers who know both ML and hardware, which is super expensive and also not as scalable. So just to dive a little bit deeper into that issues, right, in the existing workflow, right? So there's first there's an ML engineer, right, on the left. They so you imagine that we're doing a robotic product with some perception algorithms in AI, and our ML engineers train their models, develop their models, collect their data sets, curate those data sets, and then get some prototype, all iterations on cloud. And once they get a first trained model, they hand it off to a deployment team, right, or a infra team or hardware team to deploy this model on different hardware platforms, right, whether it's a GPU, whether it's robotics. And chances are the first time that happens, people will run into problems, right? Either operators are not supported, quantization has been very difficult, so the accuracy drop is not tolerable, or like the model is just too big for the memory, too big, the compute time is too long, right? So on and so forth. So then the deployment engineer have to come back to the ML engineer and saying, you know, we have these errors, we have these issues, right? So you need to fix it. So then the ML engineer need to retrain the model, and so on and so forth. So it is a very slow feedback, right? The ML engineer has to wait a couple of weeks, sometimes even months, to get the feedbacks, what's going wrong, what's going on with the design, what's wrong with it, and you know, and before they can train a new model, which takes another couple of weeks, right? So all that iterations causes slow production, slow revenue stream, and slow volume ramp up. And the fundamental of that problem, like I mentioned before, is a mismatch between training and inference, and which, you know, more fundamentally, the mismatch between the model that are being trained with the model that are efficient to deploy, right? So because these models are born in the GPU, it's not fit for these diverse hardware platforms. And, you know, we have technologies like pruning, generic pruning, or just quantization. We try to shrink the model, but, you know, because the model doesn't fit, it causes low utilization, low efficiency on the hardware. And in the end, right, there requires a lot of manual iterations, and it's not very efficient for the design. So for OmniML, our true vision, our fundamental, so our vision is that we solve this fundamental mismatch between the model training on the GPU versus diverse hardware. And we focus on the ML model itself, focus on the model architecture, right? We make the model architecture fit the hardware, make it hardware aware, make it adapt to the hardware that we're deploying to, solving that root of the problem, which in turn streamline the entire development process, get better results, get better efficiency, get better performance, and also, you know, get AI into production faster, and by solving that problem. So, and we've been, you know, since our founding, we've been working with a lot of early partners as well as early customers to test this technology in the field. For example, one of our first customer is Wise, a IoT camera for home security, and you know, we using our product Omnimizer, right? Their engineers is able to navigate through the complexity of edge hardware as well as the algorithm, and then finally, you know, get models deploy on the edge, saving a massive amount of cost on cloud compute. And also, we've been collaborating with an early partner, Qualcomm, where we actually demonstrated OmniML powered AI models on the RB5 Robotics AMR platform at Hannover Messe 2022, demonstrating that we can shorten the development process significantly by adapting the model for different platforms. So now, you know, I'm happy to you know, tell you more about how Omnimizer work, as well as you know, how Omnimizer will make this entire development process easier. So here is the you know, the workflow that we just talked about, you know, iterations, slow to production. With Omnimizer, our core product, the workflow becomes like this, right? So first, the developers still train in the cloud, right? So in their native environment within the GPU, but that during the training, it communicate with our Omnimizer platform, and which in turns actually, deploy the model onto a variety of hardware platforms hosted by ourselves, right? We can deploy these platforms and then we can measure the latency and then provide quick feedback to the ML engineer. And then the ML engineer can just do their iterations in their training environment, right? PyTorch, GPU, with additional feedbacks coming from the edge hardware, and they can iterate, right? Without involving a deployment team, without involving slow feedback. And Omnimizer takes care of quantization, takes care of a deployment process, leveraging all the existing vendor SDKs such as TensorRT, the SMP from Qualcomm, TensorRT from NVIDIA. But more importantly, during this process, right, we provide a set of services for the developer to help them optimize their model, adapt their model without knowing too much details about the hardware, which is the key to the platform, right? So I'm going to tell you with an example. Before I go there, I'm actually going to start the live demo earlier. It takes a little bit of time. So once I finish the example, I'm going to come back to the demo, and then I'm going to explain it a bit. So here is our demo notebook, which will be an interface for the developer. Let me see. Yeah, this one. So will be an interface for the developer, for the ML engineer. Right? It's a typical environment ML engineer work, and I'm going to restart all the code. And so this example, right, I'm using a DDRnet from just a basic open source repo from the DDRnet official repo, and then we are going to show how we adapt and deploy and optimize it for a Qualcomm S888 DSP. So this is the Snapdragon DSP SoC within like a mobile phone, within the S888 mobile phone, and we're quantizing it to Int8, and then we're running it directly on the phone. So now the notebook is starting, and I'm going to come back to it and introduce the results. So actually, right now we're testing the latency of the model, which takes a little while because of the network. And I'm going to come back to the explanation of that example, and then later on we're going to check the results of that live demo. So in this example, right, we're going to show how easy it is to use Omnimizer, which includes hosted service as well as a software SDK to work closely during the training, during the deployment, during the development process of this model. And in the beginning, right, so so our SDK involves a native Python API designed for PyTorch. And in the regular model design flow, we import some libraries, and then we can incorporate our optimization adaptation support during the training workflow. And then they support virtually any workflow that is based on the PyTorch. So first, we have the original DDRnet model. And we have the hardware, which is specified to be, S888 using Int8. The Int8 is actually, optional because running on the DSP, we need to the model can only be running on the Int8. And then the engine profile commands will provide the real latency tested on the target device through our service and back to the developer. So in this case, this model is trained on a Cityscape resolution 512 by 512, and we're testing the baseline latency, which is about 30.5 millisecond on that S888 platform. So this is starting point, right? Just to show how easy it is to validate the latency. Now the second step is how we start need to diagnose, right? We start, the 30 millisecond may not be satisfiable, and then we need to optimize. We need to optimize the model. We need to optimize the deployment. And in this case, we still use the hardware, and then we have another API called adapt. Right. Once we do the adapt of the model, it does a bunch of optimizations with the best effort, and also it's a white box optimization. So all of this is done to the model itself. The developer sees the original model as well as the adapted model and see what's being changed. And in this case, for the DDRNet, there's actually a very visible bottleneck in the entire model we're running on the Qualcomm hardware because there's some layers are not implemented very efficiently. And then in this case, we adapt the model by changing those layers, make them into the more efficient version of that model on Qualcomm platform. And that step alone, and then we can validate the latency with these same APIs before. And the adapted latency is now becomes 7.4 millisecond, and achieving 4x speed up. And then we can train the adapted model, separately and validate the accuracy loss. In this case, there's actually no accuracy difference because changing that, although it alters the functionalities of the model, but the behavior of the model actually doesn't change. So after training, we don't see any accuracy difference. And so this is just the first step, right? Getting this model work on the hardware, and also it can be interactive. Like I said, it's a white box optimization. We don't do things behind the scene. Anything we alter on the model is clearly visible in the PyTorch for the ML engineers. And also this step can be iterative, right? Sometimes, the issue in the original model is not that obvious. We cannot change it automatically, but by showing the developer the layer-wise latency and then some assistance, right? Some guidance, the developers can also make their own changes before heading into the next step. So now the next step of our optimization workflow, we call train and optimize, right? So this is one of the key technology that we enabled in Omnimizer. There is an Omnimize API, essentially make the model elastic, make the model itself elastic. We can make the model larger, more layer, make it smaller, smaller convolutions, less layers or narrower, whatever. So we have a starting point, which is your existing model that is written in PyTorch. In this case, the DDRNet after our adaptation, and then using the Omnimize, we get a supermodel. So this supermodel contains a elastic version of the original model, and it supports any model that are PyTorch based. And once that is done, we can then train it, train the supermodel using the original training pipeline that has been, so we don't need to alter anything in the training pipeline. We just train the supermodel as if we're training original PyTorch model. The only difference is that we need to, enlarge the training epochs to 2 to 3x of the original epoch. So it takes a 2 to 3x training time for this, but it is by doing that, actually we unlock the potential of exploring a vast design space without without 10x or 100x or even higher training cost. After the supermodel has been trained, we then can customize. We then can sample that model through a search API. So with the search API, we're able to give it a latency target, and we can sample the subnetwork from the SuperNet, and then find the best version of the latency fulfilling our constraint, and which achieve the highest accuracy, right? So this is a iterative search process running through the evaluation data sets multiple times. And our search algorithm will find the best version of the models that runs faster or equal to our target, our latency constraint. And in this case, we selected a model which is 3.5 millisecond. The key is that during this process, because the model is already trained, we don't need to retrain the model to get a real accuracy, right? So we find a version of the model that is 3.5 millisecond. We can test the accuracy on the evaluation data sets. And in this case, 3.5 millisecond model satisfies our accuracy constraint, right? So satisfies our accuracy target is actually the same as the original accuracy, maybe even slightly higher, right? 3.0 millisecond models, the accuracy will be lower. And then the 4.0 millisecond model, the accuracy is a little bit higher, so we can still make it faster. So in the end, we automatically select the submodel based on the latency target. And this submodel is a regular PyTorch model. You can then be taken into the rest of the pipeline, further validation, deployment optimization, and so on and so forth. And we can validate the latency of that model. And we can compile a device model still in the PyTorch space, but now this device model contains a handle of running the actual inference on the device, right? So by giving it the input, we can actually get on-device prediction results to validate the accuracy on device for the developer as well. So in this case, we find a 3.5 millisecond model after the search, achieving 8.7x speedup with no accuracy loss, which is a very significant increase because we find the mismatch in the model, right, doesn't work on this hardware, and also through a exploration of a vast design space, we further optimize the model. In the end, we achieve a very significant speedup, boosting the efficiency of that hardware, right? Unleash the true potential of that hardware by making the model fit, right? So, in summary, all of our optimizations are done in the PyTorch to the model itself, right? The quantization, the deployment part we use is just generic SDK, in this case, Qualcomm SMPE. We quantize the model, and then we run the model on the device without reinventing all of those parts. All of our magic happens during the model training, during the model design. We make the model adaptive. Okay, so now let's come back to the demo. Hopefully there's no problems. As we can see, right, so we've been running through the demo. We first get a model from checkpoints from DDRnet, and we specify the deployment target, and then we get the latency. So in this case, the latency we got from that original model is 30.5 and 30.5 millisecond. And the second step, as I talked about, is the model adaptation. And we get the adapted model, which is just a PyTorch model. And using this, we're profiling the model, and then we're identifying a bottleneck. In this case, we show the bottleneck in the original model. There's actually, you can see, it may be slightly small, but there are two pooling layers, right? So there's two average pooling layers that is actually taking up quite a significant amount of time in this model. But after adaptations, we reduces the pooling layers time significantly, removing that bottleneck, and we show how are you doing that. So this is actually not so uncommon, right? So for a lot of the accelerators, right, for a lot of the DSPs, they have a different support of the kernel sizes. When the kernel sizes is too large, right, for the pooling, things start getting inefficient, right? The onboard cache is not enough. You have to swap it between the DDRs, DRAM, and so in the end, actually it causes a huge performance bottleneck. But a very simple trick is just to decompose that large pooling into a couple of smaller pooling. Right? It's not the exact mathematical equivalent of the original model, but right, if you understand the model architecture, you know that this actually doesn't change the behavior of the model, and so we can do that swap easily. Similarly, there's another layer that is a kernel size 17, and we decompose it with 3 kernel size 5 models. Now, the different parameters, right? The paddings, the sizes may take a little bit of more thoughts into coming up. That's why we automate this part for the developer, right? But the idea is that as an ML engineer, you don't need to understand why that inefficiency happens, right? How the hardware behaves, right? This is it's very difficult. Different hardware have different behavior. But with this like added layer of abstraction, we provide a very a developer-friendly, right, PyTorch native, cloud native interface for our developer. And for some reason, the latency of this adaptive model is still running. So actually, I'm going to come back to my backup window, which I ran before this presentation. So I'm going to come down to it. Yeah. So after the adaptation, the latency is 7.3 millisecond, and then we start the model optimization, right? These Omnimize and then the training. And obviously, I'm not going to run through the entire training and search because it takes a while. So we're showing you the APIs, Omnimize. By the way, this step actually doesn't take a lot of time. We are constructing an internal representation of the model in our infrastructure such that we can perform this SuperNet, or we call it OmniNet training, and in the backseat. And we specify the latency targets, and then we run through the search, like I showing before. So here, I'm just going to, so in this demo, we're just loading the checkpoints from the previous successful training and then the search. And we can also do this in the workflow, right? After the search, we can just checkpoint the new version of the model or the search model. And later on, we're going to integrate that with, all the MLOps functionalities and make sure it, we can just manipulate these models as we do in the existing workflow. And then we export the subnet as PyTorch, and then we run it in evaluation mode, and then we test the latency again, right? So we show the original latency as well as this new latency that we got. The new latency is 3.8, and then the original latency is there's some like fluctuation every time we test it, but you get the idea. And then after we get these models, being a white box optimization, right? The developer can validate the model accuracy. In this case, we're just showing graphic examples. We provide some helper functions to compare the models. First, we compare the original model and then the search model. So these are both PyTorch model. Original model is original DDRnet, and then the search model is the one that we narrow it down to about 3.5 millisecond. And this subnet, and then we can just run through a sample inputs to it, and then we can compare visually the difference, or we can run through the evaluation data sets to get like the MLUs or the other metrics. Now, we can also run the validation on the device. So we first compile the device of the subnet, compile the subnet on the device. And then we can just call that subnet on device as if it was a regular PyTorch model. But actually, this prediction, this inference happened on the device. And then once we get a prediction, we can do the same cross compile as before and show visually the difference. We can also run through an evaluation pipeline and to make sure that there's no accuracy degradation whatsoever. So that concludes the demo. Just giving you an example of the developer experience of leveraging Omnimizer to adapt any existing models, right? This model can be you're developing right now, or you're getting from like open source. We don't need any specialization of the model. It can be just any PyTorch model. But then our Omnimizer APIs are plug and play, right? We integrate a few lines of codes into the process, and then we can take advantage of this new addition design experience. I'll come back to this, check out people's questions and comments. So coming back to the presentation with the conclusion, right? Our product, Omnimizer, bridges the gap between development and deployment, right? It is not your regular MLOps platform where we solve that core mismatch between model and hardware, and then we can solve it in an automated fashion, in a semi-automated fashion. And our interfaces are designed for ML engineers, right? For people who work on models, who train their models, but who not necessarily have all the intricate knowledge of the deployment hardware. And we basically sit between PyTorch and a variety of hardware platforms, hardware vendors, SDKs. It can be NVIDIA, it can be Qualcomm, it can be Umbrella, which is the three platforms that we're currently supporting. But later on, if we're trying ST electronics, MCUs, we're trying other ARM-based SoCs, as long as that vendor has a workflow of getting a PyTorch or Onyx model into deployed, right? They have an SDK themselves. We can integrate that with our engine and provide it with the developer. So, the value, faster to production, friendly, easier development experience, and is self-serving, giving developer full control. We don't modify the model behind the scene. Developer have full control of the optimizations, of the search phase of the model. And, we achieve faster inference speed, and then we unleash the true potential of existing hardware, right? So you can get, in this time, 8x, right? Some other time 2x, 3x. You can get more out of your existing hardware without the need to upgrade to the higher end, or you can, maximize the potential of the hardware. You can get more capability of the same hardware and increase the potential of your AI application. So I think that concludes my my tutorial. And right now we're actually releasing the alpha version of Omnimizer next week. If you're interested, sign up for early access. Contact us, at our email address, product@omniml.ai. Let us know, what's your pain points, what's your use case, and how can we help? Yeah. So with that, I will answer a few questions.
There's a couple of questions for you there, Dee.
Yeah. Yeah, the first question is there a sample notebook or GitHub repos which we can use to learn the OmniML platform? Yes, once you sign up, we will be sending you this information. Because right now it's still an early access version, so we are going to work with you a little bit on that. And what types of models are supported, like CNN, RNN. Right now, we support any CNN model. And we're also working on transformers, which will be coming out in the later release. Yeah.
There is one question which just popped up just now. Any plans to support Arduino?
good question, right? If I remember correctly, Arduino has that SDK for PyTorch, right? So as long as that is, we should be able to support it. Yeah. So stay tuned. We let us know, and then we'll get that supported for you.
Okay. Thank you very much, Dee. I'd also like to thank our strategic partners for continuing to sponsor these talks. They're all really super interesting. Our executive strategic partners are Arm, Edge Impulse, Qualcomm, Sentient. Our platinum strategic partners are DeepLight, ClickAttack, Reality AI, Renesas, Sony. Our gold strategic partners, Analog Devices, PhotoHub, Microsoft, NXP, Seed Studio, SenseML, and ST, and Synaptics, and SynSense, and our silver strategic partners, who you can read below. And thank you very much. That brings us to the end of this session, and hope you'll join future sessions as we have them.